Welcome back to Introduction to Machine Learning. I'm Ludwig Botmann. In this video I will speak about some further classification losses that are perhaps used a little bit less often, such as the Hinge loss or the L2 loss on scores, the exponential loss and the AOC loss. We have seen that the 0-1 loss is a very intuitive loss, but it's not well suited for direct optimization as it's not differentiable, not even convex and not even continuous, right? So the Hinge loss tries to use the good intuitive characteristics of the 0-1 loss, but approximates this in a continuous and convex form, even if it's not continuous differentiable. So here you see the 0-1 loss again. We plot as before on the x-axis the margin. So all the classifications on the right-hand side are correct classifications, and all classifications on the left-hand side are wrong classifications because the sign of the score does not match the true target. So targets are -1 and +1 in this case. Okay, so we have the 0-1 loss, and the Hinge loss is 1 minus the margin. So this thing here, but clipped to 0 if we have negative values. Okay, so in the end, we have this thing here as Hinge loss. It's only 0 if the margin is larger than 1, so here it starts being 0, which also means that in the area between 0 and 1, this is the area where we are correctly classifying, so the sign of the score and the label are equal, but we're not very confident, right? Because the score is rather small. So the Hinge loss also penalizes this a little bit, so forces the classifier a little bit to be confidently correct in its predictions, right? So we want to be a little bit further away from the 0 value here. We can, for example, use this in support vector machines, because also there we want to have some margin around the decision boundary where we have not that many points. Well, and Hinge loss is because it resembles a door hinge. Okay, second alternative is taking the Hinge loss but just square it right away. So it's also 1, 0, and it's also 0 for all values that are 1 or larger than 1. But for this linear part here, it's a little bit different. So we have a parabola part here, which means that in the so in this area here, where we are predicting, classifying correctly, but with low confidence, the squared Hinge loss penalizes a little bit less. So we are punishing not confidently, but correct predictions less than with the Hinge loss without the squaring. But then on the other hand, here it has this overshoot here, which makes it a little bit less outlier sensitive. Sorry, a little bit less outlier robust, so a little bit more outlier sensitive than the Hinge loss. But the good theoretical property is that now it's continuously differentiable, whereas the usual Hinge loss without the squaring, of course, is not differentiable at this point here, right? But with the squaring here, we are approaching with a derivative of 0 from left and right. Okay, we can analogously to the Breyer score on probabilities specify squared loss and classification scores. So again, y is -1 and +1, so that we can plot the thing here with the margin. And it turns out that, well, we can just use the scores here, the difference of the scores, and then just square these residuals. And as you can see here, we can write that in that form, which we need for plotting it in terms of margin, right? Or for expressing it in terms of margin, and that helps for the plot. So here for values up to 1, it's the same as the squared hinge loss. It's just 1 minus the margin and then squared. But for values larger than 1, it's very different, because the squared hinge loss is then clipped to 0. But the squared loss on scores not. So this goes up again. So which is really weird and very undesirable, because this means if we have very confident correct predictions, this would be penalized by the squared loss on scores. Okay, so that's ridiculously bad for a loss function, I would say. So yeah, I would advise against using squared loss on scores. Then we can add one other loss to the same plot here. That's the exponential loss. The formula is here, exp of minus the margin. So this is this line here. This is also continuous differentiable. It's convex, so it's easier to optimize than the 0,1 loss, of course. It perhaps also approximates the 0,1 loss somehow smoothly, but in a different form than the hinge loss or the squared hinge loss. It is used a lot in boosting, especially in ADA boost, which you will see in the chapter on boosting. And well, yeah, it approaches 0 a little bit slower than the hinge loss, right? Because we have these values here, or it's never exactly 0. So it's always better to be even more confident. So for the hinge loss, it doesn't really make a difference if you have a score of 2, 4, or 4,000, right? It's always a loss of 0. Not so much for the exponential loss. It gets better the more confident we are. Okay, and then the last loss, which we cannot plot in the same plot because we can't express it in terms of the margin, is the AUC loss. AUC is mostly known from evaluation of binary classifiers, right? So we need the number of negative and positive samples, and the AUC can be written with that formula here. So we always look if positive observation has a larger score than a negative observation. If so, that's good. If not, that's bad. So, but if so, it's good, and this indicator function is 1, and then we average over all these indicator functions to get the AUC. Best AUC would be 1, of course. Worst would be 0.5, right? Not 0. 0.5 is like the random classifier. But this thing here is not differentiable with respect to f due to this indicator function here. We can try to fix this by approximating this indicator function by the distribution function of the triangular distribution, which would then look something like this. So minus 1, 1. This starts here, grows here somehow, and is 1 at 1. The indicator function is of course also 1 there, so it's a smooth approximation of that indicator function, and we could use that, but still it's numerically somehow difficult. I would recommend rather to use some more common loss and to use AUC for tuning, for example. So if you have hyperparameters to tune, you can use AUC for tuning those hyperparameters, but for the ERM part, the risk minimization part, the training part, we would rather suggest you use a rather common loss function or one of these more advanced loss functions that you've seen in this video. If you want to see more on advanced loss functions, check out this paper. It's a very comprehensive survey and a good read.